So very good morning to one and all. Welcome to VLSI class once again. So in the last class we discussed about the scan-based technique, right? Now let's go to the most very important topic, that is built-in self-test technique. Okay, built-in self-test technique. This is also called BIST. This is also known as BI, built-in self-test technique. So the name itself indicates that the built-in, that means the circuit the circuit itself consists of a testing circuit. Okay, the circuit consists of a testing circuit. So whenever the error exists, the circuit itself correct that error and then test the error in this case. That is, so that's why it's called a built-in self-test. Okay, the built-in test, basically what happens is the parts of the circuits are used to test the circuit itself. Okay, the parts of the circuit are used to test the circuit itself. Okay, so in the built-in self-test, so some part of the circuit is used to test the circuit by itself. So there are two types of built-in self-test. One is the online BST bits, that is the online built-in self-test, and the second one is called offline built-in self-test. So in an online built-in self-test, basically it is used to perform the test under normal condition, normal operation. Okay, so this can be used to perform the test under normal operation. Similarly, the offline built-in self-test used to perform the test in the offline mode. Okay, used to test in the offline mode in the circuit. So there are basically the main important circuits or modules that is required in the built-in self-test are, the first one is called, the most important circuit is known as PRPG, that is pseudo random pattern generator. Okay, pseudo random pattern generator. So another one is called output response analyzer. Okay, output response analyzer, we can call ORA. Okay, the most important thing in this case, the most important parts in this is pseudo random pattern generator and output response analyzer. These are the most important parts in this circuit, and this is the circuit under test. Whenever you want to, so the circuit under test here. So what are the circuit now we are having in this case? So the main, so here the main roles of this circuit will be given in this figure. So, and the implementation of both these two circuits, the PRPG, that is the pseudo random pattern generator, and also output response analyzer, can be done by using linear feedback shift registers. By using linear feedback shift register, we are going to construct, we are going to implement these PRPG and also ORA. Okay, that is the main. It consists of two main important blocks, and to implement these two important blocks, we are going to use linear feedback shift registers. Okay, so now, so linear, let us go for the pseudo random pattern generator. Okay, first we go for the pseudo random pattern generator, and what is the structure, and we can see in this case. So to test a circuit, basically what happened, we require some test patterns. Okay, and this test pattern can be generated by using pseudo random pattern generator. Okay, by using different pattern generators you are having. The first one is different pseudo random pattern generator, and another one is called weighted test generator, and also we are having adaptive test generator. Some are in other way also we are going to generate a test pattern. There are different test pattern generations will be possible, available. So in this case, first one is called a pseudo random pattern generator, and a weighted test pattern generator, and also adaptive test pattern generators. So that means we are going to, now in this case we are using pseudo random pattern generator. Okay, so this pseudo random pattern generator uses linear feedback shift register technique. Okay, linear feedback shift registers. Okay, that means here the circuit is the linear feedback shift register is shown here. Okay, this is the linear feedback shift register circuit. Okay, so now, so as you know that to reduce the chip area, we are going to use data compression technique. Okay, we are going to use the data compression technique, and these techniques are used to compare the test responses, that is compacted test responses instead of using entire raw test data. Okay, we are going to use some compacted test data. Okay, response of the circuit instead of using entire raw test data. So here, the most important compression technique uses here is the signature analyzer. Okay, the most important technique in this case we are going to use signature analysis. We are going to use a signature analyzer basically. So here we are going to use that type of signature analysis we are going to use here. So this signature analysis is based on the concept of a cyclic redundancy checking. Okay, this is based on the cyclic redundancy checking. So basically it uses a polynomial division. It uses the polynomial division which divides the polynomial representation of a test output data. Okay, polynomial representation of the test output data by a characteristics polynomial, by using a characteristic polynomial, and finds the remainder of the find the remainder as a signature. Okay, and find the remainder as a signature, and this signature is then compared with the expected signature to determine whether the device or test is faulty. Okay, so that is the main thing. So first we are going to analyze the signature. We are going to store the signatures, and whenever the circuit under test is placed, so we are going to take the signature here, and we are going to compare these two signatures, the fault free and faulty. Okay, if the two are different, okay, faulty and are different, then we can say it is a faulty circuit. If the signatures are same, then it is a fault free circuit. Okay, so remember that point. So in this case, we are going to use a compression technique. That is the main drawback of this compression technique is there is some losses in the fault coverage. Okay, in the signature analysis, that is we are going to use analogy, we are going to use the compression technique. So in this compression technique, there is some losses in the fault coverage. That means the fault, if there is the output of the faulty circuit is matched with the output of the fault free circuit, there is a chance. So we are having a chance that in the signature analysis, that the compression technique, there is a chance that the output of the faulty circuit, there is a faulty circuit is matched with the output of the fault free circuit. So that what happened, whatever the fault is there, that is undetectable. Okay, that goes undetectable in the signature analysis. So such type of phenomenon is called, we can call it as aliasing. That is the main drawback. That means the drawback of the signature analyzer is the aliasing. So that aliasing is very drawback in this case. Okay, so sometimes because of the compression technique in this case, we are going to compress the data so that, so what happened, the signature, some data is losses here. Okay, some faulty data, some faults will be goes undetectable. Okay, that is the main thing you have to remember. And in this case, the simple form of this signature generator basically consists of a single input linear feedback shift register. Okay, the simple generator of this signal analysis is uses single input to linear feedback shift register. We are showing here. That is number here in this case. So this is the signature analysis, simple register. So in this case, so here, or what are the latches you are going to use here? Just observe, these are the different latches you are using here. Okay, So these latches, and by seeing the symbol, we can say that these are the edge triggered. Okay, they are nothing but edge triggered in this case. The latches are edge triggered. In this case, the signatures, basically the signature is the content of the register after the last input is sampled, has been sampled. Okay. Okay, whatever the content of the registers, in this case, nothing but the signature when all the last bit of the data is sampled in this case. Okay, when the last bit is sampled, last bit of the data is sampled, whatever the content of the register is nothing but it is the signature of the signal. Okay, so basically this concept of the signature, that is the signature, basically what happened. There are some input signals. Basically, we are going to represent the input signal by using polynomials. That is the polynomial we can call g of x, and that is g of x. And similarly, the output sequence you can call it the q of x. Okay, that means we are going to represent the polynomial will be like this: g of x is equals to q of x into p of x plus r of x. There is nothing but what the meaning is. We are going to divide this g of x by p of x. We are getting the quotient is q of x and the remainder is r of x. Okay, so that means we are going to divide the g of x. Okay, that is the input polynomial, we can say. Okay, and this is the characteristic. We can call p of x is the characteristic polynomial. We can divide the g of x, the input polynomial, by the characteristic polynomial. After division, we are getting the quotient is called q of x, and also we are having the remainder called r of x. Okay, and this r of x we can call it the signature. Okay, we can call it as a signature in this case. Okay, so therefore, for example, assume that we are having the characteristic polynomial is p of x is equal to this value, and for the 8 input bit sequence, we are assuming the generator polynomial will be, for this 8-bit input, the generator polynomial is given by like this one. That is x0, x1, x2, x3, x4, x4, x6, x7. So this is x to the power 7, x to the power 6, x to the power 5, and this is x to the power 4. And there is no x3 term because it's 0. And this is x square, x to the power 2. And x1, x to the power 1 is not available, it's 0, and the last is the constant term. Okay, so this is the generator polynomial. Okay, so now we are going to divide this generator polynomial by using this characteristic polynomial. Okay, we'll assume the characteristic polynomial 1 plus x square plus x to the power 4 plus x to the power 5. So you can write in the form of higher value to lower value in this case. So therefore, we can divide this one by this one, so we can get the remainder is x to the power 4 plus x square. Okay, that is, for example, you can divide the circuit like this. So you can divide the generator polynomial by using this polynomial x to the power 5 plus x to the power 4 x square plus 1. Okay, now so dividing g of x by using p of x and follow the method in this case. So first you can write in terms of x square terms. Equation first term is x square. So what happened now? X square into x to the power 5, x to the power 7. And x square plus x to the power 4 is x to the power 6. And 2 plus 2 is 4. There is no x to the power 5 term. plus we are having x to the power 4 plus, and this one with 1, nothing but x square, and take an exclusive OR function of this one. So what is the exclusive OR function? When the two inputs are equal, you are getting 0, and this is also 0. Okay, this is 0, this is 0, and this term is not there, means 0. You can say here 1 plus 0 is 1, that is x to the power 5. X to the power 5, and these two will be 0, 0 plus 1. 1, right? Again, do the same method. Again, do the same method in this case. So what will you get? Plus 1 time. The coefficient is 1. So 1 into x to the power 5 is x to the power 5. And plus x to the power 4. Plus x to square. Plus 1 into 1 is 1. Again, take exclusive OR function 1, 1, 0, and this is x square, and this is 0, x to the power of 4, x to the power of 4, plus, and this is 0. So this is the remainder. So we are getting the remainder is equal to R of x is equal to x to the power of 4 plus x square. Okay, and this remainder can be considered as the register content, and this can be considered as the signature of the circuit. So this can be written as first 0, 0, 1, 0, 1. Okay, 0, 0, 1, 0, 1. So this is the remainder. Content of the register will be like this, because we are assuming this is the x4. Okay, and this is x3, x2, x1, like this we are going to represent here. Okay, so these are the different, that is x4, x3, x2, and x1, and x0. Okay, and this is x0, this is x0, and this is again is nothing but x5. Okay, this is the xy. Depending upon that, we are going to represent, and here it is the input pattern we are going to apply. This is the input pattern we can apply here. Okay, we can apply in the reverse direction 1, 0, 1, 0, 1, 1, 1, 1 on this pattern, and depending upon that, we can find the when all lost pattern, that is 1 is entered. So what happened? What are the content of the register is there here? That is nothing but this x to the power of 4 plus x to the power of square only. So this is the signature of the content, and this signature is compared with the actual signature. If the two are equal, then there is no fault. If the two this signature and the already stored signature fault free is different, then there is a error is there. But in this case, what happens is the main disadvantage in this case is because the compression in this case. Okay, so what happens sometimes, there is a chance. Sometimes there is a chance that the signature of the fault free and the signature of the faulty both are equal. There is a chance that the faulty signature is equal to the fault free signatures. That means in this case, what happens is whatever the fault free signature is there, that can be undetected. The fault is there in the circuit, that can be detectable. Okay, there is a drawback of the signature analyzer. Okay, and the next one you can go for the output response analyzer. Okay. So in the next, okay, to go for the output analyzer. So in the output analyzer, we are going to use built-in logic block observer. Okay, we are going to use a built-in logic block observer as a output analyzer. Okay, let's consider output response analyzer. We are going to use a built-in logic block analyzer. So here in the built-in logic block analyzer, we can call it the bilbo. Okay, this is also called built-in logic block analyzer observer. So this is also called bill block. So the basically the bilbo register is the form of basically it is the form of output response analyzer, and this can be used as a cluster of partition registers. Okay, there is the basic, and the basic circuit is shown in this figure. Okay, it consists of two control signals, and we are having four different models. Depending upon the control signal C0 and C1, we are having four different models. So depending upon that four different model, you can say that when the C0 and C1 are 0, 0, we can consider the linear shift. Okay, we can consider as the linear shift. That means when the C0 and C1, okay, C0 and C1 are this is the C0 and C1. When these two signals are 0, 0, okay. So depending upon the 0, because the AND gate function in this case, this will become 0 here. So one of the active OR gate will be 0, and these are the active OR gates will be 0 in this case. So that what happens is the circuit behaves like a linear shifting. The what are the content is there, there will be linear shifted here. And similarly, when the C0 and C1, the C0 and C1 is 1, 0, this is 1 and this is 0, it behaves like a signature analyzer. Okay. When the input signal is entered, in this case, when this condition, what are the content of the register is nothing but the signature, and these are the signature. Similarly, when both inputs are 1, 1, that is C0 and C1 are 1, 1. So in this case, it behaves like a data latch. That is the data will be latches. Okay, that is the complemented latch. You can call it the complemented latch in this case. Okay, 1, 1, it is data latch, and then when 0, 1 is applied, 0 and 1, okay, 0 and 1. So what happens is it behaves like a reset switch. It behaves like a reset. Okay, so this is the main points of the linear, 3-bit built-in logic observer. Okay, built-in logic observer circuit. So this is the signal output response analyzer used as a built-in logic block observer. Okay. Similarly, we are having another very important thing in this case is last one in this chapter is the current monitoring Iddq test. So we know that the most important technique to detect the fabrication defect is Iddq test. Okay, what are the testing of fabrication defect? We are going to use this IDD test. So, for example, if there is a bridging fault is there. So, what happens because of bridging fault, there is a large amount of current flow from the power supply to the CMOS circuit. Okay, in the CMOS circuit, what happened? Very large amount of current will flows, and this can be noticeable. Basically, it's very high, large amount of current will flow. So, this current is beyond the expected range of the leakage currents. Okay, this current is beyond the expected range of leakage current. So because, for example, let us consider the drain node of the transistor, the PNP transistor, the PMOS transistor is shorted to the VDD. Assume that the drain of the, because the CMOS circuit, we are having the PMOS transistors as well as the MOS transistors. So in the PMOS transistor, source is connected to VDD and drain is connected to the output terminals, right? So when the VDD line is VDD node, there is the drain node is shorted to the power supply. Okay. So what happens? Very large amount of current, because that indicates that there is a bridging fault between the the exit bridging fault. That is the drain is connected to the VDD bridging fault. So because of this, what happened? The current that is IDDQ, that the current flowing in the drain of the quotient DC value of the drain can be very high. Okay, very high. Even when the input signal is high compared to that high current. Okay, assuming that very large current in the circuit is when the input is high. But even when the input is high, when there is a bridging fault, what happens? There is a large amount of current which is higher than the value of the input current. Okay, when the input is high, current due to input high, when input is high. So therefore, that is because of the bridging fault. So that is like this. You can analyze in this case. Okay, when the input is high, so we can assume that when the input logic for any CMOS circuit, when the input is logic high, so there is a large amount of current flows in the PMOS circuits. Okay, when the trans is high in this case, but we are going to compare these two currents in this case. Okay, current between the drain and the drain circuits of the transistor. When the current is very high compared to the input is high, then we can say that they're assuming that there is some bridging fault exists. Okay, so that is the main thing. So like this, you can identify the bridging current. Similarly, it can also use some other fabrication defects. Okay, you can detect some other fabrication defects which are not easily detected in other tests. Okay, in other tests, some faults also not. For example, for that one is gate oxide short. Okay, that cannot be identified. That can be analyzed in this test. Similarly, the channel punch through is also used to test in this type of. We can detect this type of fault also, and we can detect by using we can detect PN diode leakage also, and also transmission gate defects also we are going to analyze by using this IDDQ test. Okay, so that is the main thing, and also this IDDQ test basically you can apply. Basically, IDDQ consists of applying test vectors and then monitoring the output current, that is the current drawn from the power supply rail. Okay, we can draw. Basically, we are going to apply the test vectors. Okay, apply the test vector, and then we are going to monitor the current drawn from the power supply rail in the DC steady state condition. So like this, you can identify the different currents in this circuit, depending upon that. We can identify the test. So basically, this requires more testing time, and also fault detection capability is greatly improved with small currents, and also by using this type of to monitor the IDQ in various part of the device under test. Okay, we are going to do. So, and also in order to design this IDQ test, we are going to consider the low static current states. Okay, basically in order to design this testability of this IDQ test, we can consider that the circuit which consists of low static states. So in case of CMOS circuits, we are having low static states. That is, full CMOS circuit will be preferred in this particular example. Because in the CMOS circuit, we are using low static current flows between the VDD line to VSS line. And similarly, there is no pull up and there is no active pull up and active pull down. So that means in the NMOS technology, we are having active pull up. Okay, but in case of CMOS technology, there is no active pull up and pull down. So that means we can prefer the CMOS circuits only. And also, the internal diode complex also not possible required in this case. Similarly, no floating nodes in the circuit. Okay, whenever you want to design this type of IDQ test, there is no floating nodes in the circuit. Floating nodes. Okay, no floating nodes is there. That means the node which is not connected to the ground terminals. Similarly, there is no degraded voltages. For example, output high. Basically, the output high means whenever there is a degradation of the signals, so output is not equal to VDD. But in this case, we are not consider the degraded output. There is no degraded output level. The example is you must have VOH, that is the output high state is equals to VDD, and output low state is always equals to 0. That means there is no degradation of the current. So this type of IDQ test will be possible in this case. Okay, that is the last topic in your fourth unit. That completes your fourth unit. You will go for the, in the next class you will go for the fifth unit. Okay, field programmable logic here. So in the next class we will go for the FPGA, field programmable gate arrays. Okay, so I'm going to stop the screen now. We'll meet in the next class.